I'm Yong Chen and welcome to our presentation, which is about smart aquaculture system. So, firstly, what is smart aquaculture system? Smart aquaculture are the approaches integrated into the aquaculture industry for monitoring, analyzing, and management proposed without changing the farming operations. Now, I'm going to talk about the breakdown of smart aquaculture. Firstly, smart feeding control system transform traditional feeders into intelligent ones that continuously observe cages or tanks, optimizing feeding times and reducing labor and feed costs. Besides, artificial intelligence and machine learning algorithms analyze large amounts of data to identify patterns that can optimize production and predict the optimal feeding times. And lastly, RT sensor technology integrated with cloud services can monitor the condition of fish farms with real-time data. And these are the background of smart aquaculture. Now I'm going to explain the history of smart aquaculture. And actually, smart aquaculture has evolved through five significant phases, transforming the industry for better efficiency and sustainability. The early advancements improved aerators and water plants, which provided better control of aquatic environments. And after that, the mid-20th century saw the development of antibiotics, vaccines, probiotics, and prebiotics, enhancing fish health and reducing disease outbreaks. And in the 1990s, it brought real-time monitoring system, enabling farmers to optimize management practices based on water quality, temperatures, and other factors. More recently, with the calculating aquaculture system, data analytics, AI, smart feeding technologies, blockchain, and IoT have emerged, revolutionizing the industry by minimizing resource consumption, improving traceability, and maximizing productivity. As global seafood demand grows, these innovations are vital in sustaining our aquaculture future. Now we are going to look at the literature review. In this literature review, we explore the potential of AI and IoT technologies in improving the efficiency and sustainability of fish farm operations. Firstly, Aquacloud, a collaboration between Hasbro and IBM Watsons, uses computer vision and AI to monitor and manage sea lice infestation in real time. After that, individualized fish monitoring is made possible by iFarm, which uses AI to track individual fish behavior, enabling targeted interventions for potential health issues. Blue Aqua, SNS, and HPE have partnered to develop a smart aquaculture solutions that connects and analyzes real-time data to optimize farm operations. And lastly, Aqualinks uses advanced technologies like 5G, IoT, and AI to improve production efficiency and sustainability. This will reduce waste and ensuring food security. And let's talk about the problem statement of aquaculture. In aquaculture, traditional methods are no longer effective for monitoring and maintaining the fish farms. Poor water quality control leads to higher fish mortality rates and lower production yields. And manual feeding practices result in unequal feed consumption, causing difficulties in maintaining the health and quality of livestock. Besides, lack of early detection and treatment of diseases due to inadequate monitoring and diagnosis methods leads to reduced yield and compromised food safety. Furthermore, the labor-intensive nature of fish farming has led to difficulties in hiring and training skilled personnel, contributing to a shortage of human resources and technical capabilities. And now, let us talk about the objective. Our project aims to develop a smart aquaculture solution to help fisheries manage and monitor fish farms effectively, achieving sustainable fish farms with the use of AWS platform. We focus on different perspectives such as better water quality management, optimized feeding control, effective fish farm monitoring, alert notifications for fisheries, and increased production with precise yield prediction. Our goal is to achieve an equilibrium and sustainability in fish farming with the use of smart technology. And based on the problem statement just now, we have proposed some solutions to solve the problems. Firstly, LT sensors are placed in fish farms to collect data on water parameters and monitor indexes for each parameter to ensure they remain within normal ranges. This reduces the frequency of water sampling. The LT sensors can detect abnormal indexes that may affect water quality and different fish species, enabling early detection and intervention. Besides, when abnormal conditions fall outside the threshold range, the system will generate an alert message to notify the fisheries immediately. Our solution also provides data analysis through visualization, enabling visualization of overall farm conditions and individual tank conditions. Now, let's look at our architecture diagram. We use 10 AWS cloud services, including AWS IoT Core, S3, DynamoDB, Lambda, Collision, SNS, API Gateway, Athena, QuickSight, and Cognito. These services work together to enable device management, data storage, analytics, and security for our system. Firstly, IoT devices collect data from fish tanks, and AWS Lambda store is in DynamoDB. Amazon Recognition helps analyze fish species, while SNS sends notifications for any anomalies. After that, API Gateway is used to connect the frontend to the AWS backend, and QuickSight provides visualization for data analysis. Lastly, AWS Cognito manages user authentication and authorization for our smart aquaculture system. Now, let us look at the future trend of smart aquaculture system. Firstly, the automation and robotics, such as underwater robots and AUVs, will perform data collection without human intervention. The predictive analysis techniques like AI, machine learning, and computer vision will optimize fish farming operations. Lastly, blockchain technology will ensure transparent and secure tracking of fish from hatchery to market, building trust with customers. These environments will revolutionize the aquaculture industry, making it more sustainable, efficient, and profitable for farmers. Now, lastly, let us look at the comparison of IoT platforms. There are four cloud platforms for IoT we discussed. They are AWS, Azure, Google Cloud, and IBM Watson. Firstly, AWS provides excellent connectivity, rules engine, development environment, and security, while Azure features device management, monitoring, and IoT edge computing. Besides, Google Cloud boasts excellent connectivity, security, and a faster machine learning service, while IBM Watson has robust device management, monitoring, security, and real-time analytics. Each platform has its unique strengths, but AWS has a large development community and a proven track record, while Azure has an intuitive interface and strong integration with Microsoft's other products. Google Cloud has the faster machine learning service, while IBM Watson provides the most comprehensive enterprise-level solution. And these are the comparison between the IoT platforms. And that's all for my part. I will pass to my teammates to continue the presentation. Thank you.
Hi everyone, I am Jendu, and now I will show how we send the aquaculture data to IoT core. First, we need to create a thing for the IoT. Once we created a thing, then we need to create a rule for the message routing. After we created the rule, we need to go to the MQTT client and paste the topic we have created in our Python script and press the subscribe. We have subscribed to the topic, and now we will send the data in the Python script. It has connected to the IoT core and the data has been published, and we will return to the MQTT client and the data will be shown here. The incoming data is then routed to an AWS Lambda function which processes the data and store in DynamoDB. We fetch the data and we can view that the data has been sent to DynamoDB. During the data storage process, Lambda also triggers SNS services to send an alert message to an email when the data exceeds the threshold set. The thresholds are shown in here. This is the email saying that the alert message has been sent. Next, AWS Group is used to crawl the data stored in DynamoDB and create a data catalog. In order to use the crawler, we need to create the crawler by pressing this button. We can run the crawler. A job is then created to transfer the data from DynamoDB to S3. Once we created the job, we press the run. After running the job and the data is now loaded into S3, the crawler runs again to crawl the data and update the data catalog in Athena. In Athena console, we select the database that we have created in crawler. Then we press the three dots here and press the preview table. The result is shown in here and saved in S3. We have using recognition services to recognize the type of fishes. If there is a fish that is not supposed to be in the tank, an alert message is sent using SNS. This is the model that we have trained. This is the sample message that has been sent by the SNS when there are other type of fish in the tank. That's all for me. Thank you.
Hi, sir. My name is Samini, and now I'm going to explain about the Cognito service, which is an authentication service used to manage the user pool when the user registers themselves from the website or mobile application, and the user pool helps to store the user data for authentication purpose. Before getting started, you need to create a user pool in the Cognito service and set up all the configurations. Since we have created before, namely Aquaculture Cognito, I will just continue on to use the user pool. And for our group, we have integrated the user pool into our mobile application. And in order for the mobile application to be work smoothly, we need to initialize the user pool ID as well as the app client ID into our repository, which is this one from our env file. Once the pool ID and also the client ID have been initialized successfully into our repository, the mobile application is now ready to be used. So I will do a demo starting from creating a new user account until the user is able to log into the Smart Aquaculture system. And here is a login system, and we can just click on the sign up now to register a user using the email address and also password. Once done, input the email address and password, can just click sign up to register the email address, and we can see that the email address has been registered to the user pool and pending for verification, so the status will be unconfirmed. So now we can just go to the email address and get the verification code. Once the verification code is input into the text field and click verify, the user pool account will be turned to confirm, means that the registered email address has been successfully registered to the Aquaculture Cognito user pool. So now the user is able to log into the system. And here's the homepage for the Smart Aquaculture system, and that's all for the Cognito service. Next is about the API gateway to query the data from DynamoDB. In order to integrate both services together, the Lambda functions need to be created, and in here, namely IoT call API Lambda. So these Lambda functions will help to call the DynamoDB table to query the data, while the created APIs and HTTP methods, which consist of post, patch, delete, and get request, has been called in these functions as well to trigger the APIs respectively based on the event occurs. Moving back to the API gateway console, as you can see, there are quite a number of APIs have been created, and I will select the IoT call single data as an example for the demo. And let's start from the get request by pressing the test button, and the query parameter we will be passing the Aqua API ID, the second ID, and click test. And we can see that the request has successfully sent. The status is 200. For patch method, we can also update the data. For example, we are having the Aqua API ID number 2 and having ammonia 0.084, and we want to change the ammonia value. So we can just pass the Aqua API ID number 2 and set the key to ammonia. The IoT value we can change to 0.098 and click test. So the API for Aqua API ID number 2 has updated successfully. We can navigate to the DynamoDB to check for the data. And we can see that the Aqua ID number 2 has been changed to 0.098. Followed by the post request, we can also create the IoT data to be stored into the DynamoDB, and we can test it by passing the body into it. The Aqua ID will be 222. So based on the result, the new ID has been created and stored into the DynamoDB, and we can also check it from the DynamoDB table as well. And we can see that the Aqua ID 222 has been created. Lastly, for the delete request, we can just delete the Aqua data by passing the query parameter with the ID number, and we can just test it. And from here, the result shows that the Aqua ID has been deleted successfully. And from the DynamoDB, we can no longer see the data once we refresh. And that's all from the API gateway testing from the console. Now I will demo the created API that has been integrated into the mobile application, whereby the admin of the aquaculture farm can build IoT parameters and also build a notification message for any warning messages. For IoT parameters, there will be a listing shown in the interface. When the admin click on it, they can view the details information about the aquaculture for the specific tank and also locations. For the notification messages, it will be similar to the IoT parameter, which will be shown in listing view. And the admin can view the warning ID whenever the IoT parameters has been triggered the threshold, so they can take alert immediately. And that's all for the API gateway.
Hi, my name is Lo Chia-Hui. I will demonstrate about QuickSight. QuickSight is the business intelligence tools that used to visualize the data. First, we need to import the dataset. For our case, we will be using antenna to import our dataset. And here we need to give the name for our data source. And we need to click on validate connection to ensure that the connection is validated. And then we click on create data source. And here we need to choose the database that we want to retrieve our data. And here we need to choose the tables that we want to visualize the data, and click on select, and then click on visualize. So here is the interface where we can use the data that we have imported earlier to draw our graph. So this is the interface that I have created earlier. We can drag and drop the data to the view wheels, and the data in the graph will change according to the data that we have provided. And here are the different types of the graph that we can use to plot our data. And for this, we can also use the filter to filter out the data that we want to view. And for this one is the aquaculture monitoring dashboard that I have created, where the user can view the data that have been collected by the IoT sensors. The above here is the overall average for different types of the data that have been collected from different IoT sensors. For our case, we have 10 different tanks to view. So the user can select on the tank that they want to view. If the user want to see the trends for the tank 1, the user can click on tank 1 and then click on see trends. And the below data will change accordingly to the data in the tank 1. And if the user want to see the details of the tank 1, the user can click on see tank details, and the user will be navigated to another page which only contains the details of the tank 1. And here the user can click on the category to view, which is the different types of the category which the user can choose to view. And the data here will change according to the choice of the user to view the data. That's all for this QuickSight dashboard. Thank you.